G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. Or maybe you just had a quick break between part one and this is part two or part B of lecture 12. So what we're doing, this is the second part of revision for assessment 3, and I've already done 7 questions. I'm going to do 7 more. So this time we'll do metric space for shape, metric space set of numbers, a continuous function, cofinite, vector subspace, Bolzano-Weierstrass, the basis of a matrix, and then a little reminder that you should have been looking at Sierpinski. Okay, so let's get into it with some questions. So here's question 1. Using relevant calculations, determine whether a square with a side length 4 units is a metric space. Now, I've just drawn 2 squares up here, which wouldn't be in the assessment if it was an exam question. I've just drawn it up here for you to think about which way you'd have the square on the XY plane. So, assuming the square is centered at 0, 0, then a relevant set of side length equations could be. Now, if it was me, I would pick either this one or this one. I wouldn't pick a square at a different angle. Now, yeah, good luck to you if you want to pick a square with a different rotation. Have fun figuring out you're sort of going to burn up a lot of time figuring out calculations for what the exact, midpoints and where it crosses over. Much easier to use something which is easier to figure out. So in this, for me, I'm just going to use this square. Could just as easily have used this square. You can pick whichever square you want. If a square was in the exam, or if it's another shape, again, pick something which is easy to figure out. So using this orientation, I made up, or I didn't make up, using this orientation with 0, 0, these are the equations. So you've got x equals 2 for y in between minus 2 and 2, x equals minus 2, again, y in between minus 2 and 2, y equals 2, for x in between minus 2 and 2, and y equals minus 2 for x in between minus 2 and 2 again. And that gives you this shape. So taking the first side length, and in this instance, you only have to take one side length, because if it applies to one side length, it's going to apply to all 4 of them, because we're surrounding 0, 0. And we want to know if it's going to be a metric space. So the first side length, the distance from 2, 0 to 0, 0 is 2. Where 2, 0 is a midpoint. So what we're looking at there is this point here. And the second point I'm going to look at is an endpoint. So 2, 2 to 0, the distance, 2, 2 to 0, 0, the absolute value is 2 root 2, where 2, 2 is an endpoint. And again, I've put a dot on it. So now you know which 2 points I'm looking at, and we can tell that this distance doesn't equal this distance. Therefore, a square is not a metric space, since the distance to the center varies along its perimeter. And really, that's all you have to do. Done. Okay. Hope that's helpful when you do the assessment. Question 2. Explain why a set of rational numbers are metrizable but not a metric space. So here I've made this sort of a double question to help you out, because you might get one part or the other part, or you might get a double question. So this is sort of 2 questions in one. To be metrizable, the set must be open and separable. So rational numbers are infinitely countable in either direction. So Q goes from minus infinity to infinity. And rational numbers can be separable. The removal of a single rational number R results in 2 open sets. So I've got from minus infinity to R to infinity, where R is one of the rationals. So this means they are metrizable. Yay, tick for that. Now we want to show it's not a metric space. However, rationals are not a metric space. Now you could do this in one step. I'm going to do all 4 steps, just so you're aware if you have to prove something is a metric space. So a metric space must satisfy non-negative distance, symmetry, triangle inequality, and completeness. So the distance is non-negative. In other words, if I go from R1 minus R2, so we've got 2 points, and that's going to equal R2 minus 1 minus R1. The distance is going to be the same, and it's not negative. And where R, I should have probably written Rn there, these elements of the rationals. Okay, my image is going to get in the way here. Every point in Q has a symmetrical point which is the same distance from the origin. So R1 equals the absolute value of R1 equals the absolute value of minus R1. So that distance from the origin is going to be the same. So there's a symmetrical point. So we've got non-negative, we've got symmetry. Next one is triangle. So the direct distance between points is always the shortest. In other words, R1 minus R2, the absolute value, is going to be less than or equal to R1 minus R3 plus R2 minus R3, where the absolute value of those, where R, again, I should have written Rn, is an element of Q. Okay, so this direct distance is going to be closer or equal to R1, where you're going through a third point. So we know that's true. And here is where we're going to fall down, which is completeness. Since you can find numbers which reside outside the space to which numbers within the space converges, that's why it's not going to be complete. For example, and if this was you doing it, you should give an example. You should just make that statement. You should give an example. A part of the rational number space can exist which converges to, say, and I've given an example here, root 2, but root 2 is not in that rational space, hence it is not complete. So you could create a set of numbers from the rationals which converges to root 2, but root 2 isn't in the space. So that's why it's not a metric space. So there you go. Question 3, image down the bottom, and we'll keep going. Okay, the following is a definition of a continuous function. fxy, 0, 1 to 0, 1. What is the problem with this definition? Look carefully. Give you 5 seconds. 4, 3, 2, 1. Hopefully you picked it up. Answer. 0, 1 is elements of 0, 1, the closed set. The closed interval is compact. It contains both its endpoints. 0 is an element of 0, 1 here, but 1 is not an element of 0, 1 because the open interval on this end, hopefully that's what you picked up, is not compact. The interval only contains the first endpoint. Therefore, no function can exist which is continuous. So hopefully you're paying attention there. Okay, question 4. Let P be the infinite set of all real numbers except for the set 2, 4, 6, 8, 10. Its complement T is the set 2, 4, 6, 8, 10, which is finite. Is P cofinite? Explain. Answer, yes, P is cofinite since the complement T is finite. Pretty simple. And you would have seen it before in lectures. Question 5. This one I've taken directly from a lecture as an example because I thought it's very similar to the question in the assessment and just a reminder to you of this sort of thing. So prove that V, which is x1, x2, x3, is an element of R3 where you've got this rule x1 minus 2x2 is 0. It's a subspace of R3. So proving that this is a subspace of R3. So we're going to let A equal A1, A2, A3, then A1 minus A2, A2 is 0, and B, B1, B2, B3, then B1 minus 2B2 is 0. So you've got to prove the 3 things. 1, it contains a 0 vector, so that's pretty easy. If we set all of A to be 0, then 0 minus 2, 0 equals 0, so it's true. So V contains a 0 vector. Satisfies vector addition. And again, this is pretty straightforward. You can tell by looking at the equation if it's going to satisfy vector addition and matrix multiplication or vector multiplication. If everything is scalar, then it's going to work. If you've got some value in here which is like x1 squared, you're going to be like, oh, okay, this is going to be a problem. So if this is all scalar, it's going to work. So satisfy vector addition. A1 plus B1, A2 plus B2, A3 plus B3, then this minus 2 of these equals, and here I've just separated into A1 minus 2A2, so you're getting this equation separable. You've got this, and then you've got it in B's equals 0 plus 0, which is 0. So it satisfies vector addition. Satisfies vector multiplication. So no, we're going to let Cn equal some new combined constant of An, Bn, and so I did state in the lecture, it's better if you state this up front. So here I've got AB where A1 B1 equals C, A2 B2 equals C, C2, A3, B3 equals C3, then we can say this equals this equation. And here, probably better here if I refer back to saying, therefore it satisfies this original equation. Maybe put a red star on it and say satisfying the red star equals 0. So therefore, okay, image in a way. Therefore, V is a subspace of R3. So pretty straightforward. Okay, next one. Question 6. Does the following set satisfy the Bolzano-Weierstrass theorem? Explain 0, 1. So round brackets mean it's an open set. So does it satisfy this theorem? Answer, yes. The theorem states every bounded sequence of real numbers contains a convergent subsequence. Now, you've got to be careful in how you read this bounded sequence. Now, is an open set 0, 1 bounded? Answer, yes. Even though the open set between 0 and 1, both 0 and 1, even though the set is an open set between 0 and 1, both 0 and 1 can be shown to be bounds of the sequence, despite being outside the actual set. The theorem does not require the bound to be included in the set, i.e., the set does not have to be compact to satisfy Bolzano-Weierstrass. So because you can prove that this is bounded by 0, this is bounded by 1, therefore it's a bounded sequence. Therefore, Bolzano-Weierstrass says it must contain a convergent subsequence. And just for your information, because you'd really like to know this, there's another theorem called the sequential compactness theorem, which states every sequence in a closed and bounded subset of Rn has a convergent subsequence in that set. Now, if you've done any research, which you might not have, and you've found Bolzano-Weierstrass theorem is true, then obviously it's like, duh, of course that's going to be true. It's like saying this window is made of glass, therefore there is some glass inside the window. It's like, yeah, well, thanks for sharing. So we didn't study this particular theorem. If I examined this, if I made up a question on this in the assessment, I would state this theorem so you could read it and just think about it. But yeah, that's another theorem that exists. Like I said, throughout the course, there are multiple different ways and constant research you can keep on doing. Anyway, there's another theorem that says it's closed and bounded, but just be aware for Bolzano-Weierstrass, it does not have to be compact to satisfy Bolzano-Weierstrass. Okay, question 7, last one for this video is, and this is straight out of a previous lecture, but we're going to do another one, is 1, 1, 2, 2, and 1, 2, 3, 4, I've missed out the zeros, a valid expression for a basis of matrices in M 2 by 2? And the answer, of course, you know, is going to be no, because dim, or the dimension, is 3. 1, 2, 3. You can only get 3 things out of that. You can change this number, you can change this number, you can change one other number, but you can't change the fourth number to be something else because you've only got 3 matrices there to fiddle around with. You need a fourth one to offset that. So let's do that. Is this, with 4 matrices, a valid expression for a basis of matrices in M2 by 2? Look carefully and think. 5, 4, 3, 2, 1. And the answer is no. Hopefully you've figured out why. Have you figured out why? Hopefully, since matrix number 2, this one, and matrix number 4, this one, are linearly dependent, it means that dim is still 3. So effectively, this one with its 3's is the same as this one because I can get this one by multiplying by a scalar to equal this one. So it's linearly dependent, which means the dimension of this set is still dim 3. That's the dimension, it's still dim 3. So it's not valid as a basis. Okay, so just pay attention to what's written in the assessment because that might happen to you. Okay, last one, just a reminder, make sure you research Sierpinski space and how the Sierpinski triangle can be considered a metric space. I'm going to have to move my image up again because I've got some triangles there. Just to remind you, there's the Sierpinski triangles, deleting the center space each time. Okay, that's it for that's it for this video. See you in part C. God bless you. Stay safe and keep studying. Okay, bye.